Good morning and welcome to the full paper session number 4 on volume and vector computing and representation. My name is Hamish Carr. I'm the session chair, and as you're probably aware by now, we will be having video presentations followed by a Q&A, which you can participate in by either the YouTube or through the Discord channel. So our first paper this morning is Local Extraction of 3D Time-Dependent Vector Field Topology by Lutz, Hofmann and Filip Sadlo, and it will be presented with Lutz Hofmann. So please, Lutz, can we roll the video?
Hi, this is Lutz Hofmann. I'm a PhD student with the Visual Computing Group at Heidelberg University, and I'm going to present our approach to local extraction of 3D time-dependent vector field topology. A steady 3D vector field assigns a 3D velocity to each point in a three-dimensional domain. Vector field topology considers the separation of streamlines, which are tangent curves of this vector field. The generating structures are the critical points, which are isolated points of vanishing velocity, and the saddle type critical points exhibit attracting and repelling stream manifolds, which separate the domain into regions of similar flow behavior. Time-dependent vector fields vary over a finite time interval. There we are interested in the separation of path lines, which are time-dependent trajectories that additionally depend on an initial time. As we are going to discuss, the counterpart to critical points in this case are hyperbolic path surfaces, which exhibit attracting and repelling streak manifolds, which take on the roles of the invariant manifolds from steady vector field topology. Separation of trajectories is measured by the finite time Lyapunov exponent. For steady vector fields, the hyperbolic ridges in the FLE fields are consistent with the invariant manifolds of steady vector field topology. If we first consider the case of a saddle type critical point where the two negative eigenvalues are equal, then the forward FTLE field exhibits a ridge line. This ridge line intersects with the ridge surface in the backward FTLE field in the critical point. In the structurally stable anisotropic case, it turns out that the forward FTLE field also exhibits a ridge surface. Now these two ridge surfaces intersect in a line which we call a bifurcation line. These are special streamline segments that exhibit attracting and repelling 2D manifolds. They do not need to contain a critical point, and they can also be closed. We found that in cases where a steady 3D vector field does not contain any critical points or periodic orbits, we need to include bifurcation lines in order to be consistent with ridges in the FTLE fields. In 3D time-dependent vector fields, the FTLE fields now depend on initial time. This means that FTLE ridge intersections move along path lines, which we call hyperbolic trajectories. In the anisotropic case, such FTLE ridge intersections are lines that move along path surfaces, and we call these hyperbolic path surfaces. These are the generating structures of 3D time-dependent vector field topology. And obtaining them is the main challenge. The method that we are going to use is, in the isotropic case, we use paths of critical points in a suitable frame of reference as initial candidates and apply the method proposed by Yuzhe and colleagues to refine these paths toward hyperbolic trajectories. This method is based on computing the localized flow and its fundamental solution matrix along these initial paths, and use the singular value decomposition to obtain refinement directions in the attracting and repelling directions along these paths. And this method can be iterated until it converges toward a hyperbolic trajectory. In the anisotropic case, our candidates are paths of bifurcation lines in a suitable frame of reference, which we need to refine toward the hyperbolic path surface. Now, since there are dynamics tangential to this surface, the direct refinement of the entire surface would be challenging, which is why instead we consider surface streamlines and refine each of these lines toward hyperbolic trajectory, which then span the hyperbolic path surface. In previous work, Lagrangian coherent structures, which are the main organizing structures of fluid flows, were defined as a subset of the ridges in the FTLE fields. This has led to direct visualization approaches and extraction approaches of the FTLE ridges. The problem with these approaches is that computing the FTLE fields is very expensive and it has to be repeated for each time step of the dataset. This is why Sadlo and Weisskopf for the 2D case and Oeffinger and colleagues for the 3D case proposed to compute FTLE ridge intersections in single time steps and extract the hyperbolic trajectories and hyperbolic path surfaces by path line and path surface integration. The problem with that is that this integration is numerically unstable because in both forward and backward time there are repelling manifolds involved. Methods that overcome this avoid this integration altogether and use a refinement of initial candidates. The first of such methods was proposed by Yuzhe and colleagues who considered paths of critical points in the lab frame and refined them toward hyperbolic trajectories. This method has a straightforward extension to 3D time-dependent vector fields, which, however, as we are going to see, misses large parts of the Lagrangian coherent structures. Machado and colleagues proposed to use Galilean invariant space-time bifurcation lines for obtaining hyperbolic trajectories in 2D flows, which overcomes problems with using the lab frame in certain flow configurations. Last year we presented an approach that combines the displacement invariant frame of reference proposed by Roche and Günther with the refinement scheme proposed by Yuzhe and colleagues to obtain a more accurate time-dependent vector field topology for the 2D case. In this work, we would like to extend our previous work to 3D while being consistent with hyperbolic FTLE ridges in the 3D case, whereas Oeffinger and colleagues already have shown that one, instead of hyperbolic trajectories, needs to consider hyperbolic path surfaces. We furthermore are going to present an approach to automatic determination of seeding lengths that are involved in the streak generation. Other approaches to time-dependent vector field topology include the streamline and pathline oriented topology as proposed by Theisel and colleagues, who consider the temporal evolution of critical points and periodic orbits, as well as local properties of path lines. Ferstel and colleagues seeded streak surfaces on FTLE ridges in order to obtain separating streak surfaces where they make use of the advection properties of these FTLE ridges. Roche and Günther propose to extract steady vector field topology in a displacement invariant frame of reference. In our method, we propose to extract candidate lines, which we then refine toward hyperbolic trajectories, which typically are going to span hyperbolic path surfaces. Having obtained these, we construct seeding structures, from which we then compute streak manifolds in the space-time domain, such that we obtain a description of the separating structures over the entire time interval. For the candidate extraction, we compute a Galilean invariant frame of reference defined by the feature flow field, and we found that instead of directly computing the feature flow field, either by inverting the spatial Jacobian or by computing an eigenvector of the space-time Jacobian, it is numerically more stable to minimize a temporal derivative over all possible Galilean transformations in local neighborhoods following the method proposed by Günther and Theisel. Having obtained these frames of references, we extract bifurcation lines and saddle-type critical points at each time step of the dataset. These are then triangulated in the 4D space-time domain using a simple algorithm based on ball pivoting. For this, we advance a triangulation front based on a distance criterion in order to obtain the triangulation. In the next step, we project the space-time flow onto this surface and compute surface streamlines, which we then refine toward hyperbolic trajectories using the method proposed by Yuzhe and colleagues. Having obtained the hyperbolic trajectories, we compute the streak manifolds using a specified seeding length. In previous work, this seeding length is user-defined and it needs to be chosen small enough. However, in actual numerical datasets, we found that due to the limited time interval that's available, we actually would like to choose this seeding length as large as possible while still yielding meaningful structures. And by meaningful, we mean that the separation along the streak manifold should be at least a specified percentage of the separation at the hyperbolic trajectory. So we proposed the following method. First, we compute a streak line along a maximum user-defined length, and we compute it as a space-time stream surface. Having obtained this space-time streak surface, we compute the localized FTLE in reverse direction at the endpoints of the path lines contained in this surface. This gives us a regularly sampled mapping from the initial segment to the streak line and allows us to determine the optimal seeding length such that the separation along the obtained streak manifold is at least a percentage of the FTLE at the hyperbolic trajectory. Let's have a look at an example. Here we see that if we choose this percentage too small, we obtain streak lines that correspond to very weak separation, while if we choose the percentage too large, we miss important features of the flow. In our experiments, we used a percentage of 50%, which we have found to work quite well. Now, having obtained our seeding structures, we can compute the streak manifolds. First, let's discuss the case of a single hyperbolic trajectory which has a one-dimensional and a two-dimensional seeding structure. From the one-dimensional seeding structure, we compute a space-time surface, and from the two-dimensional seeding structure, we compute a space-time volume. Time slices of these space-time objects then yield the streak lines and streak surfaces over the entire time interval. A hyperbolic pair surface can be regarded as a set of hyperbolic trajectories that each has such a pair of a one-dimensional and a two-dimensional streak manifold. Their union yields a pair of two two-dimensional streak manifolds, which we can extract directly as space-time stream volumes in both time directions, and again the time slices give us the streak surfaces over the entire time interval. Let's have a look at these synthetic datasets that each represent the structures that we consider in our topology. A structurally stable isotropic saddle is necessarily a spiral saddle point, and in the anisotropic case we have bifurcation lines that either contain a critical point or they don't, and they can also be closed. Now we take these steady vector fields and make them unsteady by translating them along a curve, and the unsteady counterpart of our steady topological structures are hyperbolic trajectories and hyperbolic path surfaces as shown below. The streamlines in the steady case are now replaced by path lines, and the invariant manifolds from steady vector field topology are replaced by the streak manifolds in our time-dependent topology. Our method is constructed in a way such that applying it to a steady vector field, the steady vector field topology is recovered. For an actual application, let's have a look at a numerical simulation of a fluid behind an obstacle where the inflow velocity is varied linearly along the obstacle. Here are shown the candidates and their refinement toward the hyperbolic trajectories, which are near FTLE-rich intersections. We compare our topology with the steady vector field topology in steady reference frames as proposed by Roche and Günther, and we found that their more expensive computation does not reliably yield better candidates than the Galilean invariant one. Also, their topology is not well aligned with ridges in the FTLE fields because their computation is local in space and in time. Next, we compare our time-dependent topology with the direct extraction of ridges in the FTLE fields. Here we compute the FTLE in a small area of our dataset for different resolutions. And we see that for low resolutions, there is aliasing in the extracted ridge surfaces, while at higher resolutions, false positive FTLE ridges appear that need to be further filtered out. We now compare the distance of our streak manifolds to the FTLE ridges, and we see that it decreases as FTLE resolution increases, which means that the FTLE ridges converge toward our streak manifolds for increasing resolution of FTLE. Comparing our method with the straightforward extension of the 2D approach, we find that this method would miss large parts of the ridge surfaces visible in the FTLE fields because it only considers single hyperbolic trajectories instead of hyperbolic path surfaces. Next, we consider a dataset of a numerical simulation of airflow in a closed container where the air is heated at the bottom and cooled at the top, and we found that most of the time-dependent topology is generated by a single strong spiral saddle type hyperbolic trajectory that slowly moves near the center of the domain. This dataset is particularly difficult to analyze using the FTLE because many of its ridges are induced by shear and do not correspond to hyperbolic separation. Finally, let's have a look at these two numerical simulations of a flow behind an obstacle. In these two datasets, the Reynolds number is increased, which corresponds to increasing turbulence in the flow. This example shows that our candidate extraction is not robust with respect to turbulence. However, the streak surfaces are still attracted toward LCS, which means that they are still somewhat aligned with the ridges in the FTLE fields. This example shows that for future work, there is a need for a better suited reference frame or other heuristics in order to obtain initial candidates for computing hyperbolic trajectories. This concludes my talk. To summarize, we have presented an approach to 3D time-dependent vector field topology, which is consistent with hyperbolic FTLE ridges, or the LCS. Our approach generalizes steady vector field topology, where we additionally include bifurcation lines. Our approach is based on a local extraction of candidate lines and surfaces, which we refine toward hyperbolic trajectories and hyperbolic path surfaces. We have also presented an approach for the automatic selection of seeing lengths that are required for computing streak manifolds. With our approach, we obtain a generative representation of the LCS over the entire time interval. For future work, as already mentioned, there is a need for a more robust extraction of candidate surfaces, and we would also like to consider an extension to shear-induced and elliptic structures. Thank you for your attention. I'd be happy to take any questions now.
Thank you very much, Lutz. And I will say it's nice to see progress in this area because it's one of the areas that we really need good tools in. I'm going to ask if anybody has any questions, but I don't see any so far, so I shall start off with a question for myself. In the paper, you've got some performance figures that indicate for a roughly 60 cubed data set, your computation takes something like an hour and a half. What are your thoughts on how best to get this running faster so you can handle bigger data sets?
So in our prototype, we didn't optimize
anything for performance that much. And of course, the local extraction is trivially parallelizable. You could even do some parts on the GPU or on large clusters, like especially the local computation of the reference frames and the extraction of the paravectors, lines, and critical points. However, the more global, the refinement part is global and requires to iterate over the entire data set, or at least the regions where the features are located several times, and that would be more challenging to speed up.
Okay, do you have any sense of how you could minimize the communication between blocks if you were doing that? How much of this can be done relatively locally is the question.
But every hyperbolic trajectory you can compute isolated, so there's no communication needed. And typically a hyperbolic pair surfaces is made up of like many hundreds depending on the resolution. So this would be easy to do. Okay. I'm more concerned about the data. If the data is too large, you would run into trouble there.
There's a concern about the runtime, as you can see, but one hopes that we'll find ways of improving that. Did anybody else have any questions? Well, in which case I will ask another question, and you did touch on it. What are the failure modes? In other words, when does this break completely and give you a nonsensical answer?
Well, we heavily rely on having a heuristic to predict where the hyperbolic trajectories are going to be, and so far it works quite well if it's not too turbulent. So if it's somewhere in between completely laminar and more turbulent. As you have seen in my presentation, for more turbulent flows, it gives some features, but clearly misses many of them.
That's an interesting observation. So what you're saying is that the more turbulent the flow, the more difficult it is to apply this in practice because you still have to find the heuristic. Yes. And that implies that there's potentially a rich area of improving heuristics for turbulent behavior. Yes?
Yeah.
Okay, thank you. I don't see any other questions, so I'm going to suggest that we move on to the next presentation after thanking Lutz for his presentation. Thank you. Thank you and welcome back to this session on volume and vector computing representation. Our second talk is on parameterized splitting of summed volume tables by Christian Reinbold and Rüdiger Westermann. And Christian will be presenting this talk, and at the end of it, we'll have a Q&A session. So let's roll the presentation.
Welcome to our talk about parameterized splitting of summed volume tables. Providing real-time exploration functionality in large numerical datasets is a challenging task, in particular if large subsections of the dataset have to be accessed at once by a single user operation. Examples are statistical queries on 3D medical or spatiotemporal meteorological data with 2 spatial and 1 time dimension. In the past, specialized acceleration structures based on summed area tables, short SAT, have been developed to support fast aggregation over arbitrary rectangular domains. However, these structures usually come with a significant memory overhead. In this talk, we are presenting yet another SAT-based data structure that can flexibly trade speed for memory and also improve significantly on existing techniques. So, summed area tables originate from a work of Crow in '84, where summed area tables originally were proposed as an alternative to mipmaps in texture mapping. The idea behind them is to pre-compute and store partial sums for all axis-aligned rectangular areas starting at the lower left corner of the dataset. These sums are called prefix sums. They are the entries that are stored in the SAT. For instance, we can see here the entry 5 in the SAT, which is just the prefix sum over the box starting at the lower left corner and going up to the corner indicated by the position of the 5. By the inclusion-exclusion principle, arbitrary axis-aligned rectangular sums can be recovered from 4 prefix sums by summing up the prefix sum for the top right and bottom left corner and subtracting the prefix sums at the other 2 corners. So here we can see that 7 plus 1 minus 3 minus 4 equals to 1, which is just the sum over the blue box shown on the left. This concept immediately translates to datasets of arbitrary dimension m, giving rise to some volume tables, or short SVT. Here, 2 to the power of m prefix sums are required to compute a sum over any axis-aligned rectangular solid. The advantage here is that the cost for sum computation does not depend on the subsection of data that is summed over, and summation is equally fast for small and large subsections. The downside, however, is that prefix sums become large and require high precision when storing them. For this reason, storing a sum volume table of a dataset of size O of n requires O of n log n memory. In particular, for data with 3 and more dimensions, often containing billions of values, memory consumption quickly becomes an issue. For a binary dataset of 1k to the cube, the sum volume table takes 31 times the memory of the original dataset. Previous works by Isan et al., Zellman et al., and Mishra addressed this issue by pre-computing and storing either less prefix sums or storing specific partial sums of relatively small size, from which any prefix sum can be reconstructed by fetching a limited number of pre-computed sums from memory. In general, the more and larger the pre-computed sums become and thus require more memory, the less fetches are required to recover a prefix sum. Whereas previous approaches have fixed memory consumption for a given dataset, our approach allows to flexibly trade memory consumption for the number of fetch operations, so that any memory constraint larger than the actual dataset size can be satisfied while still providing highest possible performance. The remainder of the talk is structured as follows. First, we present hierarchical SVT data structure design that allows to influence the characteristic quantities, memory consumption, and fetch count by various parameter choices. Second, we show how these quantities are computed from the parameters. And third, how to find parameterizations such that the budget of memory consumption or data fetches is not exceeded while minimizing the respective output quantity. Last, we compare results to existing methods. So we start with a hierarchical SVT data structure. Our data structure evolves around the core concept of splitting a volume such that any prefix sum of it can be derived from 2 prefix sums of smaller shape. So take this example of a binary 16 times 4 times 3 volume. We define a split dimension and then place axis-aligned cut planes that are perpendicular to this direction. Along these cut planes, we cut the volume into blocks. And now we process each block individually. Here, we sum up values along all bands of the block that follow the split direction. This yields a slice of aggregate values. Then, we cut the block in half. Whereas the front part remains unchanged, the rear half is mirrored at the cut plane, and then its last slice is removed. As a result, we obtain 2 subarrays and 1 aggregate slice. This process is repeated for all blocks except for the last one. The last block is added to the set of subarrays, and the aggregate slices are stacked to obtain the so-called aggregate array. By considering 4 different cases, one can see that any prefix sum of the initial volume can be recovered from a prefix sum of the aggregate array and a prefix sum of one of the subarrays. In the first case, the box of interest ends immediately in front of a cut plane. Here, we can recover a prefix sum from an aggregate array only, since the box partitions into bands that were summed over in the aggregate array. In the second case, the box of interest now ends in the last block. Here, we sum up all values up to the last cut plane by taking a prefix sum of the aggregate array. The remaining values are collected by querying a prefix sum of the last block. In the third case, the box of interest ends in the front half of another block. And here we proceed similarly to the previous case. The sum of all values up to the last cut plane intersecting the box can be recovered from a prefix sum of the aggregate array. The remaining values are considered by computing a prefix sum of the front half of the block the box ends in. Now to the fourth case, where the box of interest actually ends in the rear half of the block. Here we extend the box of interest up to the subsequent cut plane and compute prefix sum from the aggregate array. Since the box is oversized now, we subtract the extended part again by querying a prefix sum from the mirrored rear half. Note that the mirrored process is required to express the extended part as a prefix sum instead of a postfix sum. We conclude that the split process allows us to store multiple small sum volume tables instead of a single large one, effectively reducing the number of bits that are required to store an SVT entry in memory. However, this comes at the cost of now fetching 2 values from memory per prefix sum computation. But there is no need to actually stop here. The arrays obtained from splitting can be split again to reinforce memory savings at the cost of additional fetches. For instance, one could decide to split all subarrays of width 3 again. And when all splits are applied, for each block, either its data or its sum volume table is stored in memory. Formally, such a split hierarchy is described by a parameter tree. For each split, an internal node with 2 parameters is generated. Here, k indicates the split dimension. In our first split, that is k equals to 1. And z, on the other hand, constrains the length of all subarrays to either z or z minus 1 in direction of the split dimension. The cut planes are then placed such that these constraints are fulfilled. In the first split, we can see that all subarrays have length 3 or 2 respectively, hence z is 3. Additionally, each internal node has several subtrees, where the first subtree describes how the aggregate array is processed, the second subtree describes how the subarrays of length z are processed, and if z is larger than 1, there is also a third subtree that describes how subarrays of length z minus 1 are processed. In this example, we store the aggregate array as is in memory, hence the first subtree contains a single external node. Subarrays of length 3 are split again, so that the second subtree starts with an internal node describing the split. For the subarray of length 2, the sum volume table is stored. We express this by an external node with a ZSVT flag. The parameter tree for the second split is expanded in the same way, however, with a small difference that there is no third subtree since z equals to 1. Now with the parameter tree at hand, we answered the question how to compute the memory footprint as well as the number of data fetches required for recovering a prefix sum. The algorithm to do so proceeds in 3 phases. In the first phase, the top-down phase, we propagate shape information into the leaves as well as information about the maximum possible value of a block that can occur when setting all data entries in the initial volume to the largest expressible integer of 2 to the power of the precision of the dataset minus 1. Also for each split, we record at the edges how many subarrays of length z and how many subarrays of length z minus 1 are obtained. So we can have a look at this example here, where we can see that the maximal value for the aggregate array rises by a factor of 7, because the bands we sum over have length 7. On the other hand, for the subarrays, the maximal value stays at 1. Further, we see that we obtain, by the first splitting process, 4 subarrays of width 3 and 1 subarray of length 2. Of course, we can do this propagation also for the next internal node, and then have all information at the external leaves that we require. Then next, in the evaluation phase, the information at the leaf nodes is used to compute a memory consumption as well as an upper bound for the number of fetches when querying a prefix sum from a leaf block. In the bottom-up phase, we propagate this information back into the root node. Memory consumption is obtained by adding up the memory requirements of all subtrees. On the other hand, an upper bound for the number of fetches is obtained by taking the maximum of fetches for both subarray subtrees and then adding the fetches for the aggregate subtree. This reflects that a prefix sum of the block before splitting is recovered from a prefix sum of the aggregate array as well as a prefix sum of a single subarray after splitting. Note that this bound does not have to be tight, as we discussed further in the paper. So have us have a look at the example. Here we can see that the number of fetches for the second internal node is 10, which is just the sum of the fetches here 9 from the subarray and the aggregate array 1. Further, the memory requirement of 72 bits is just 45 plus 3 times 9. Now, we continue this propagation phase into the root node, and here the memory of 480 is achieved by summing 72 plus 4 times 72 plus 1 times 120. And the fetches, on the other hand, are obtained by taking the maximum of 10 and 1, which is 10, and then adding another 24 fetches for the aggregate array. Until now, we have not discussed how parameter trees are generated. This gap will be closed now. Given a budget of either available memory or number of data fetch operations, we will identify a parameter tree that satisfies the given budget and minimizes the other unconstrained quantity. Conceptually, we can think of parameter trees as being two-dimensional points where memory consumption and fetch count is mapped to the point's coordinates. When doing so, we end up with a large scatter plot where each point represents a possible parameter tree. The parameter trees we are interested in are those for which no other tree exists with both smaller memory footprint and fetch count. These are the optimal parameter trees, here shown in green. Their points follow a memory performance trade-off curve that tells us how much memory one requires at least when having a fixed number of fetches available. In an ideal world, we could iterate the optimal parameter trees along the memory performance trade-off curve and then select the one that maxes out on the given budget. We did exactly this with an implementation following the branch and bound paradigm that is commonly used to solve combinatorial optimization problems such as this one. It allows us to find optimal parameter trees for small volumes, e.g. 64 to the cube binary volumes, but it does not scale to large volumes that we are actually interested in. And this is not really surprising, as combinatorial optimization problems tend to be NP hard, and we assume that this is the case here too. The way we deal with this is by designing a heuristic that may not return optimal parameter trees, but at least it returns trees that are close to the aforementioned trade-off curve. It comes with two parameters, the volume shape n and a control parameter lambda. The parameter tree returned by the heuristic is guaranteed to require at most lambda fetches, and it also requires less memory the higher lambda is chosen. If we have fixed budget of either memory consumption or fetches, a suitable parameter tree can be found by applying a discrete root finding algorithm to the function that maps lambda to a value of how much the parameter tree returned by the heuristic over or undershoots our given budget. So let us have a look at the heuristic. For lambda equal 1, we just store the data in a classical sum volume table. If lambda exceeds the number of data value entries, the data is stored as is in memory. In all other cases, the heuristic will create a split. Here, the split dimension k is the dimension in which the volume extends the most, and the subarray length parameter z is obtained by interpolating between the smallest and largest value for z, and then rounding the result to the next reasonable integer. The interpolation function itself depends on lambda and has been derived by fitting it to a small-scale optimal parameter tree configuration computed by our branch and bound algorithm. With k and z defined, the shape of the subtrees are known, and the heuristic can be used recursively to populate the subtrees. However, we still have to define control parameters lambda a and lambda z for the heuristics invocation. By requiring that lambda a plus lambda z equals lambda, we ensure that the final parameter tree does not require more than lambda fetches. The ratio of lambda a to lambda, one aims for, again is determined by fitting a function to small-scale optimal parameter trees. Please refer to the supplementary material of our work for more details about the fitting functions. Now that we have discussed all components of our data structure, how does it actually perform? First, the quality of the heuristic is evaluated by comparing heuristically determined parameter trees with the optimal ones returned by the branch and bound implementation. We do so on a small-scale scenario of a 64 to the cube binary volume in which we computed all optimal parameter trees in 12.5 hours. The blue line is the memory performance trade-off curve of optimal parameter trees, and the green line is the curve obtained when running the heuristic with different values of lambda. Except for a fetch counter value of 4, memory consumption of heuristical parameter trees is only slightly increased compared to the optimal memory consumption. Now, we compare our approach to related work mentioned in the beginning of the talk. We assume a 1k to the cube binary dataset. In the graph, the lower black horizontal line indicates the dataset size, and the upper line indicates the size of the classical sum volume table. The memory performance trade-off curve that is obtained by sampling the heuristic is shown in blue. The results of the reference methods are indicated by colored crosses. As all crosses are located to the top right of the curve, we can conclude that our method outperforms all of them regarding both memory consumption and number of fetches. When targeting similar memory consumption as the reference methods, our approach yields the results indicated by colored dots. We are able to reduce the fetch count by a large magnitude. For instance, we require at most 40 fetches instead of 952 fetches by 3D Fenwick trees, which is a decrease of over 95%. Equally, when targeting similar fetch count as in the reference methods, we are able to reduce memory consumption by at least 50%, and similar results are obtained for different volume sizes, such as 256 to the cube, 2k to the cube, or 8k to the cube. In particular, when increasing volume sizes, our approach becomes even more interesting since reference methods start to become unavailable due to their fixed memory requirements. As of yet, our work does not address some issues that have to be solved in future work. For instance, there is no GPU implementation yet. However, in order to compete with GPU-based encoding schemes of reference methods, it will be required. Further, we did not investigate on the influence of prefetching and caches on decoding speed. Instead, we assumed that the number of fetches actually is a good indicator for performance. One can also think about optimizations such that sparse data is stored efficiently in our data structure as well. Currently, memory consumption is similar for sparse and dense data alike. Lastly, we plan to extend our work to nominal data by combining our approach with other approaches, such as the mixture graph of Altelaya et al. This concludes the talk. Please check the paper for further evaluation results. There, we conduct a qualitative comparison of features that are desirable by volume data structures, and we also present a quantitative comparison to the work of Yuzhe Lu et al., which shows similar performance as our approach when memory consumption is equated, but comes with a list of disadvantages related to fitting one-parameter models to SVT chunks. Thank you for listening.
Thank you for that presentation, Christian. One of the pleasures of being a session chair is that in the absence of questions asked by the audience, it's my job to come up with the trickiest ones that I can, just to make sure that we're doing this properly.
Okay.
So in the interests of exploring the outer limits of this method, one of the questions that is occurring to me is that the number of bits you need probably depends on the details of the data. And therefore, there might be a relationship with the information theoretic entropy of the data in your tables. Have you considered that possibility?
So no, we have not thrown information theory on this. So what we just assumed is that, okay, we need at least as many bits without encoding to store the largest number. This is the largest possible entry that we propagate in the parameter tree. So we assume, okay, we now data has like precision of m bits. We just say, okay, in the worst case, all these largest values in the dataset really occur. So it's just constant values of, let's say, 255 for an 8-bit dataset. And then we see what is the largest numbers that can arise at least. And then we just take as many bits for each of these small blocks in the external leaf nodes. So there probably is, if you want to depend on the data set and not only, or if you want to depend on the content of the data set and not only on the shape and its precision, there's probably a lot of room where you can even go further and try to apply less bits as we do.
Thank you. That does raise another point, which I believe is at least partially covered in the paper, but which didn't show up on the slides, and that is that clearly the number of bits is easy to determine where you have integer data, but maybe trickier when you have floating point data. So how do you handle it when you have floating point data?
So we first said this in the talk, no, not again. When you have float data, or even if you have negative integer data, we just force the user to do rescaling, proper rescaling to, let's say, if you have float values from, I don't know, -10 and 100, then you have to squash them all together into a domain of 0 up to the highest precision that you want, and then you discretize. So you have to round. And the reason behind that, yes, you have rounding errors, but when you think how some volume table actually works, and your float ranges are really large, let's say you have half of the data set is really small data and small values, and half of the data set is really high. And when you're rescaling and round, you probably lose all the details in your data, which has data of smaller magnitude. Some volume tables fail in this case generally because of floating point precision. When you do this kind of, I take the top right corner, subtract the top left corner, add the top left corner, and subtract and add the corners. You have cancellation effects there. So when you have these kinds of large different magnitudes, that rescaling floating points to integers does not work for you, you probably are basically in trouble for all some volume tables, and also with our method, of course.
And also potentially you may have trouble with the numerical representation in the first place.
Exactly, yes.
And that, in fact, was what was starting to trigger me about the information theoretic entropy, was realizing that to a certain extent, the volume tables techniques depend on having your floating point values in a reasonable range, whatever reasonable means. Yeah. Question, does reasonable relate to entropy? And that was what was triggering the other question.
Oh, okay. Yeah, I only have thought so far that, okay, this is a limitation, but classical SVTs doesn't solve them either. So I do not do it as well, to be honest. So
yeah, but
I probably have no real answer for that.
I was thinking about underlying causes, and that there might actually be a reasonable explanation why this is a necessary limitation on the set of techniques.
Yeah.
So information theoretic entropy was what came to my mind. I'm sure there are other possibilities. And that was why I was following up that line of questions, if that makes sense.
Okay, yeah.
Thank you for answering. You've given me some more insight into the methods. I still don't see any other questions, and I think we're about ready on time to move to the next presentation. So thank you very much for the presentation, Christian.
Yeah, thank you too.
Thank you again, and we've now got the third talk in this session, which is compressive neural representations of volumetric scalar fields by Lu, Jiang, Levine, and Berger. And Yuzhe Lu is going to be doing the presentation, and then again there will be a question and answer. And I would like to encourage somebody other than myself to ask some questions.
Hi, I'm Yuzhe Lu from Vanderbilt University, and my co-authors are Kairong Jiang, Joshua A. Levine, and Matthew Berger. I'll be presenting our paper, Compressive Neural Representations of Volumetric Scalar Fields, where we propose a new approach to compress large-scale field-based data. The visualization of large-scale field-based data is a fundamental component to many post-hoc analyses. As our ability to simulate and acquire data grows, the need for compressing these gigantic volumes for visualization purposes also grows. For field data, and in particular scalar fields, they are often produced by high-performance computing simulations and require a high spatial and temporal resolutions to accurately resolve domain-specific features of interest. As a result, these data often has a large size that poses many challenges to visualization, ranging from bandwidth constraints, disk storage, data accessibility, and interactivity. In this work, we propose a learning-based method for compressing scalar fields, which encodes the data with a coordinate-based neural network. This method is compressive as we represent a scalar field with a learned function that is parameterized by a set of weights whose size is smaller than the field size. Our approach follows a standard compression setup that comprises of two steps, an encoding step and a decoding step. During the encoding step, we encode a provided scalar field with a coordinates-based neural network, where the network is tasked with predicting the field's value x indexed by ijk. More formally, we aim to minimize the following mean squared error loss, where pi is a sample point in the volume. In this loss function, when the subscript d equals to 3, this represents a scalar field whose domain is a 3D Cartesian coordinate system, while d equals 4 may represent a time-varying scalar field in 4 dimensions. During decoding step, we can reconstruct the sampled field simply through function evaluation, where the input can be either grid vertices or arbitrary positions. In recent years, lossy compression of large-scale volumes has been an important topic, and previous research can be largely divided into 3 lines. The first is transform-based methods. These techniques enable compression by allowing the end user to separate features within a transform space, which removes high frequencies while preserving low frequencies, and ultimately specify the data representation. The second is data feeding based. Data feeding is related to our neural network-based approach, but the method to achieve the fit is different. Broadly, this approach considers the trade-off between how many samples are used and how much precision is devoted to each sample. The third is deep learning-based methods. Recently, numerous researchers have deployed deep learning techniques and used neural networks to enable a variety of visualization tasks. While their applications are different, all of these works share a common thread in that they construct representations that blend visualization tasks like rendering and interpolation with data representations. Closely related to compression is the task of super-resolution, for which many techniques have been developed in the computer vision communities. In fact, many of these techniques are tested against possible compression techniques, but none were specifically designed for compression. Thus, while they are compressive, their main strengths lie elsewhere. What's more relevant to our work is the idea of implicit neural representations. Recent work has demonstrated the potential of networks consisting of fully connected layers as continuous and efficient implicit representations for modeling a variety of data. A sample work is Deep SDF by Park et al., where the authors represent 3D shapes implicitly with a learned continuous sign distance function. We utilize a similar approach in our network design, as it has been shown that this design can achieve superior performance. Notable recent works that also informed our network design include using periodical activations and Fourier feature mappings. More specifically, we're extending the network design called Siren, where the sign is used as a periodical activation function, which can be expressed as this formula. Based on this previous work, we take advantage of the following techniques and designs to build our compressor. We build a network consisting of fully connected layers with periodical activation functions, and parameterize it based on field size and desired compression ratio. To further compression gains, we perform quantization on weights. We also use gradient information as a form of regularization and add residual connections to make the network more robust. Overall, our compressor is conceptually very simple and straightforward, as you can see in this diagram. The core component of our compressor is setting up our network and performing under parameterization. Given a data volume and a compression ratio, we compute the desired number of weights for the network. Together with network layer L, we derive an integer k such that the network, consisting of mainly for the connected layers and periodical activation functions as the first layer with weight in shape k by d, intermediate layer L layers with weights in shape k by k, and the final layer with weights in shape k by 1, such that these total number of weights sum up to approximately m. Compression is achieved as the network will be the compressed field and its weight size m is smaller than the field size. We also use residual connections in our network to tackle the vanishing gradients issue in training as we increase the number of network layers. If residual block in our network takes the form above, omitting bias vectors for clarity. Here, AI presents a vector of activations from a previous block I. I plus 1 is a vector of activations at the next block I plus 1, and I plus 1 is a pair of learnable matrices associated with block I plus 1. We just justify this design with the following plots. With residual connections, as the network depth increases, the training stabilizes and we obtain a boost in performance over non-residual connections. So far, we have been assuming that the network weights and volume are of the same precision. In fact, further compression can be gained through quantizing the network weights. Since the first and last layers of the network are parameterized by small weight matrices, we found through experiments that they require high precision for good performance. Thus, we do not quantize these matrices. Instead, we find that most of the parameters of our network exist in intermediary layers that are parameterized by matrices of shape k by k, and that distribution of activations in these layers take on a specific form. Specifically, we find that distribution of weights in each of these layers take on approximately a normal distribution with slight variations, thus making them amenable for quantization. Thus, it is these matrices that we quantize. Moreover, we want to point out that empirically, deeper layers have lower spread and a higher concentration of values around 0. We then move on to cluster these weights with k-means. What remains is to decide the number of clusters. We set it based on the precision at which to present the weights. Namely, if we wish to represent the weights with the precision of bits, then the number of clusters will be set to 2 to the power b. Empirically, we found that quantization might lead to drop in performance that is dependent on specific volumes. Here, we show this impact with two network options with their corresponding quantized representations as dashed lines, setting b to 8. Thus, we run experiments to find the number of bits that offer a good trade-off between the number of network weights and level of compression. In the rightmost figure, we plot the PSNR for a sequence of networks with approximately the same compression ratio. We increase the number of bits used for quantization along the x-axis and compensate by decreasing the number of weights of the network. We observe that 9 bits at 512 clusters, the network takes a minimal drop in PSNR, and similar results are observed in different volumes. Thus, all networks in our work represent weights of intermediate layers with 9 bits. The use of sinusoidal activation functions in our network also implies that we can take arbitrary order derivatives of the function. Thus, we can optimize for the derivatives of the function, in addition to just the provided field values. Specifically, we can modify our original loss to ensure that the spatial gradient of the function is close to provided gradients of the original scalar field. Here, x prime denotes the provided scalar field gradient, and we set lambda to 0.05, which we found to give a good balance between the gradient and scalar value fit. In some cases, x prime may be accompanied by the field. In other cases, we may numerically approximate gradients using finite differencing schemes. Note, however, for certain volumes, like acquired medical images, the estimated gradients may not be reliable for regularization. Here, we show the impact of gradient regularization by showing isosurfaces for the reconstructed jet volume. We can clearly see that the gradient regularization helps to suppress erroneous high-frequency details, as highlighted in the yellow circles. Now, after the encoding step, let's have a closer look at the neural decoder. As previously mentioned, once the network has been trained and the volume encoded, decoding is rather straightforward, as it amounts to evaluating the neural network. Beyond reconstruction, a key advantage of neural scalar field representations is the support for random access function evaluation. We may evaluate our function at any position, not just grid vertices. Thus, the network can serve as an interpolant. Furthermore, the need to numerically estimate derivatives can be eliminated as we can compute higher-order information from the network directly. The network now acts as an oracle for querying the function that can be called by traditional realization pipelines. As an illustration, we have developed a neural volume renderer with our network, where at each step of remarching, we evaluate our network at all current ray positions to obtain function values. Moreover, it is trivial to support direct illumination via the computation of function gradients as we remarch, which is then normalized for shading purposes. Also, it's worth pointing out that, as shown on the right, the quality of the volume-rendered images suggests that our network serves as a good interpolant, not merely overfitting to the sampled field's value. To evaluate our approach, we run our method on a variety of datasets on different levels of compression. Moreover, we compare our method to the state-of-the-art compression technique, T-thresh, a method for compressing arbitrary tensor data. Note that we limit our comparisons only to where T-thresh has already demonstrated superior results to a variety of existing compression methods. The main evaluation metric we use is PSNR, which stands for peak signal-to-noise ratio, and is calculated as the following, where Dmax and Dmin refer to the max and mean field values, and RMSE is root mean squared error. Basically, the lower the mean squared error of the reconstructed field versus original field, the larger the PSNR and higher overall precision of reconstructed data and thus more accurate post-analysis. First, we show the quantitative results where gradient regularization is not used. Note that as T-thresh accepts an error tolerance like PSNR rather than compression ratio as input parameter, we run T-thresh for a sequence of PSNR values such that they give compression ratios that are roughly in the range of what we consider. For 3D scalar fields compression, we find that our method is largely an improvement over T-thresh, with the only exception being the jet volume for low compression ratios. In particular, we found that our method obtains larger gains in performance in high compression ratio realm. These suggest that when our networks are under-parameterized, they remain robust and can still obtain a good approximations to the given scalar field. We also show the superiority of our approach on time-varying scalar fields using the asteroid data on top row and Isabelle data on the bottom row of varying compression ratios. The compression ratio are denoted in x/y at the top of each subplot, where x is the compression ratio of our approach and y is the compression ratio of T-thresh. As the figure shows, our approach achieves superior results on asteroid dataset when compared with T-thresh, with more stability on both ends. In part, this is due to the fine resolution of sampling in time, where the simulation evolves very slowly. For the Isabelle dataset, our method performs comparable to T-thresh at low compression ratio, except for the start and end time steps where we outperform, as shown in the bottom row. For higher compression levels, however, our method gains larger boosts in performance over T-thresh at all time steps, showing the preference of our method for high compression ratio scenarios. Qualitatively, we show volumes compressed at different level by our approach, where top row is the original volumes, the mid row is medium compression, and the bottom row is high levels of compression. We find that our method has minimal degradation in performance as we increase the compression ratio. Next, we will show some visual comparisons between our method and T-thresh. On the left is the comparison for the magnetohydrodynamic simulation. For high compression ratios, we find that our method produces smoother results and can better retain features in the volume. On the right is an evaluation of our method on the extreme compression ratios for the RT dataset. We find our method gracefully degrades in performance, whereas T-thresh tends to produce high frequencies. Finally, we show how gradient regularization can be used to produce better behaved scalar fields in comparison to prior works. As previously mentioned, the effect of gradient regularization will be prominent when isosurfacing the volume. We show isosurfaces for the RT dataset here with our gradient regularized network and T-thresh. Though both have roughly the same PSNR, our method suppresses high-frequency details, as highlighted in the yellow circles. Although our method can achieve state-of-the-art results for compressing scalar fields, we acknowledge several limitations. The primary drawback is the high computation time for training. In the left figure, we plot training times as a function of compression ratios for 3 scalar fields of different spatial resolution. Perhaps counterintuitively, as the compression ratio increases, it takes less time to compress the data, due to the fact that higher compression ratios utilize smaller network architectures. We intend to address this limitation in future work by investigating multi-resolution methods for training, adapting our network to take spatial locality into account. A major benefit of our approach to compression is that we do not need to store the entire volume in memory at once, since during training, we need only access random samples of the field. Addressing limitations in the time required to train will enable us to realize this benefit. In addition, our method faces limitations in handling noisy volumes, such as those produced from medical imaging. The main issue is not in capturing the predominant features of the volume, but rather in preserving the noise itself. This is also problematic for gradient regularization, where it is challenging to extract useful gradient signal for our network if noise is present. On the other hand, we demonstrated that simple finite difference schemes for simulation data proves helpful for regularization, and we expect higher order numerical schemes for derivative estimation should also prove useful. Beyond gradients, we can also regularize the learned function with any type of differential expression, and this can lead the way to preserving the physics associated with a given simulation as part of a compression approach. Despite the limitations, we're optimistic about the use of neural networks for scientific data compression. Besides the clear advantage as shown over other architectures, coordinate-based MLPs offer significant flexibility in designing constraints for data preservation. In future work, we may show that certain networks can better preserve a variety of features in volumetric data. Finally, I would like to thank my co-authors, Matthew Berger, Joshua A. Levine, and Kairong Jiang. Without them, this work would not be possible. You can find the code for our work following this link on GitHub. And our work is generously supported by NSF and US Department of Energy. Thanks for listening.
Thank you very much for that presentation, Yuzhe. I note that there are questions in the chat this time, so I will start off by simplifying the first one to ask the following question. One of the parameters to this computation is effectively the choice of how you design the neural network in the first place. And you've taken one of the current standard methods for designing that neural network. Have you considered how much difference that choice of neural network makes?
Yeah, the architecture of the neural network definitely plays an important role in compressing the data. But when during the time I wrote a paper, it's still kind of siren the architecture I just mentioned. Pure fully connected layers with periodical activation functions still seem to be the best way to seem the best architecture. More recently, however, I have came across this work. So instead of have a giant network, what they do is that they kind of have a really shallow MLP, but they have a kind of coarse grid of features. And these the vertices of these coarse grids, they have kind of latent features. It turns out this method works really well as well, but we don't fully understand why this works. So yeah, again, the choice of a neural network architecture definitely plays an important role, and they will make a difference in the quality of the compression.
So that's a line of follow-up that can be done at some point.
Right.
Okay. The second question that was raised was that you've mentioned that in the noisy acquired data, such as medical imaging, the gradient estimation can be challenging. Are there other things that can be different in that type of data compared with simulated data? How much does that affect them?
Yeah, so I would say the difference between simulated data and acquired data matters a lot right now to our approach. So when we design our network, we mainly have simulated data in mind, and when we try our method on acquired data, it doesn't work so well in a sense that for acquired data, there's a kind of noise present in the volume, and it's kind of hard, to just preserve the noise. So right now we don't have a good solution to that. So yeah, that's my.
And sometimes the best answer to a question like that is we don't know. Sometimes.
Yeah, we're looking forward to address this limitation kind of our future work. Right.
Okay. The next question was about the training and evaluation. It's asking, and I think this is going to be fairly easy to answer. What is the training data? Are the evaluations performed on the same samples of the volume as in training? How good is the network at new positions, e.g. when interpolating between time steps or samples in object space?
Sure. Let me have a look at the question again.
If I'm understanding the technique correctly, you are using the data itself for the training in the first place.
Right. So there is no kind of train test split in our case here. You can probably understand as kind of overfeeding on the training data. So basically, there's so in the reviews we kind of come across the question, does our network generalize well for the data the network hasn't seen? So our answer is that we're feeding all the data in the volume or i.e. the order coordinates of the volume to the network and train the network to get the scalar value at a specific position.
Could you then feed into the network a position off the grid, which you can compare with a resampled or interpolated value?
Right, it's a really good question. So on the regular grids, the only scalar value you can get out is a kind of regular vertex, the unit, right?
Is that because you're feeding in the x, y, z as integers?
Like I mean, for kind of more traditional methods, like T-thrash, when the compression is done directly at the regular grid, then when you want to, query the scalar value of a specific point, you fit in the energy value x, y, z in the domain, right? But for our neural network, it's kind of a continuous interpolate. It means like for the data, we haven't seen for example, a floating point position, right? Like the network is still able to.
I think we're now running out of time.
Sorry.
No, it's obviously an intricate question, so I'm going to recommend that the rest of the discussion and the remaining questions move to the Discord channel, that we thank Brian for his presentation again, and that we move on to the next presentation.
All right, thanks so much.
Thank you. We're now moving to the last talk in the session, which is on thin volume visualization on curved domains by Felix Herter, Hans Christian Hege, Markus Hadwiger, Verena Lepper, and Daniel Baum. And I believe Felix is the one who's presenting, so if we can roll the presentation.
Hi, and welcome to Thin Volume Visualization on Curved Domains. Presenting to you is Felix Herter. In classical direct volume rendering, we shoot rays from a virtual camera through every pixel of a canvas and through our dataset. The ray segments that intersect the volume will be sampled, the samples mapped to color values, and the accumulated color values will be mapped to the canvas. The result is a natural outside view of our dataset that is easy to understand and allows us to get an immediate grasp of what it is we are looking at. In the thin volume visualization technique presented here, we strive to compute a structure-aligned view into the dataset. For this, we assume the existence of two corresponding surface meshes. One, M-curved, is embedded into the volume and traces a structure of interest. The other one is flat and serves as a proxy geometry for rendering. We shoot rays through M-flat and again compute intersecting ray segments. The surface correspondence allows us to transform the ray segments into the data volume. From here, we proceed as in classical volume rendering and obtain a deformed view into the volume. Our previously curved structure now appears to be flattened out while still looking like a thin volume. When moving the camera around, the transformed ray segments adjust accordingly, which gives the impression of interacting with an actual volume dataset. The close-up illustrates this effect. This work was motivated by the virtual investigation of ancient written documents, such as this antique silver scroll on the left or the papyrus package on the right. The dense and complex geometry of these datasets limits the use of volume editing or deformation techniques. Furthermore, since the occluding element is a structure of interest itself, accessing the interior of the document through a smart adjustment of the transfer function can be ruled out. There is much related work in the visualization of complexly arranged structures in volumetric data, notably in the field of medical applications. Here, the most closely related is the work by Williams et al., in which curved planar reformation is enriched with volume rendering for the investigation of tubular structures. There, the area of interest is given by a ruled surface obtained from a curve that traces a tubular structure inside the volume. The technique presented here can be seen as an extension for the investigation of thin, curved structures, where tracing with 2D surfaces allows more freedom than tracing with 1D curves. Further, we illustrate the potential of this rendering approach by showing an initial set of interaction and investigation techniques that can be built on top. So how does it work? As mentioned before, we assume the existence of a surface mesh M curved that traces the structure of interest inside the volume. We further assume the existence of a second mesh M flat that is in correspondence to N curved. That is, we have a one-to-one vertex correspondence and according one-to-one edge correspondence. For the presented examples, we will show how we generated these surfaces, but this is not part of the contribution and different datasets are likely to require different techniques. Given the two meshes, we want to transform intersecting ray segments in an adequate manner from M flat to M curved. We will explain the approach for a ray segment that intersects M flat in a vertex V flat. Segments intersecting inside a triangle will be handled by barycentric interpolation of the involved entities, as is explained in more detail in the article. The transformed segment will intersect the corresponding vertex V in M curved. The rotation of the segment is computed by establishing a reference basis at V flat and rotating it adequately to fit at V in M curved. A change of basis will then compute the desired transformed segment direction. As for the transformation, the normal direction of M flat will be transformed to the normal direction at M curve. Now what is left is to compute the transformation of the x direction, as the y direction can then again be computed by applying the right-hand rule. When computing the transformation of the x direction, we want to capture the deformation from M flat to M curved. We do that by computing a least squares fit to that deformation over the two one-rings at V flat and V respectively. We start by computing a least squares fit of weights over the one ring at V flat using the concept of an overcomplete frame that has more frame vectors than a basis would have, one frame vector per triangle edge in the one ring. Because the frame vectors are not orthonormal, we need the dual frame in addition to the frame. There are infinitely many dual frames and we use what is called the canonical dual frame. This is a unique frame that results in weights with a minimum L2 norm directly corresponding to a least squares fit. These weights will be applied to the frame at V, which gives us the transformed x direction after a final projection onto the tangent plane and renormalization. On top of this rendering technique, additional tools can be built to support the investigation and understanding of the volume data. We show this for 4 applications. Consider this sketch of a volume cross-section. If we see an interesting feature rendered on a flat, we can simply mark it there where it is easy to do so and obtain the corresponding location inside the volume through the mesh correspondence. We can also ask which other areas are close to the selected area inside the volume and visualize that information back on a flat. Or, secondly, assume that the curved surface does not perfectly trace a structure of interest. For thin isosurface rendering, we can note down the signed distance from the curved mesh to the iso value and indicate this distance with an appropriate color overlay on the rendering of N flat. Or thirdly, consider the case where the tracing is adequate, but an inhomogeneous thickness or interstructure distance leads to a sampling of adjacent material which we would like to avoid. If we can identify these areas in the rendering of M flat, we can simply paint over them and trigger through this a local shortening of the affected ray segments until we are satisfied. Or fourth and finally, we could improve an initial tracing in a similar spirit. If we can identify in the rendering that an area of the tracing deviates too far from the structure, we could again paint on the respective area on the flat mesh to trigger a shifting along the normals of the corresponding vertices in the curved mesh in an effort to improve the fit. This is particularly interesting in combination with the previously mentioned color overlay, which gives us additional feedback on the fit. So here we see that the structure is subdiving. The color changes from red to blue and eventually our structure will not be sampled at all anymore. After shifting the vertices, we expect a more homogeneous coloring. The first dataset shows a battery that was imaged using neutron tomography, and we would like to get a better understanding of the rolled electrodes. The curved surface was generated by first tracing the electrodes in 3 cross-sections orthogonal to the winding axis. The resulting polygonal chains were connected to form the desired triangular mesh that traces our structure of interest. The flat mesh was obtained by applying a near isometric flattening approach to the curved one. Here we see the final volume rendering, in which we can clearly see the whole unwound electrode at once. If we now detect something interesting, we can select it in screen space on the flat rendering and compute the corresponding patch of the curved mesh. This gives us an idea of where in the volume we are currently investigating. Next, we ask which other areas of the curved surface are close to the selected area and map this information back to the flat mesh. Next, we look at a computed tomography dataset of a southern three-banded armadillo. We would like to investigate the carapace that we see here. Again, we trace the structure of interest here in 18 cross-sections and connected the line segments to form the curved mesh. The flattened mesh was obtained with a near isometric flattening approach. On this dataset, we show a thin isosurface rendering. We can clearly see the whole carapace at once, which might be interesting, for example, for comparative investigation of multiple specimens. When we zoom in, the free-moving camera allows us to see the scales from different angles. A look from the other side reveals that we selected quite a long ray segment length, so that large parts of the skeleton are visible. There we can notice significant distortions due to the length of the segments and the general approach of casting linear rays from a curved mesh. Instead of adjusting the global segment length to a more appropriate setting, we showcase a local shortening of the segments triggered by interacting in screen space with the flat mesh. We indicate the affected area with a white circle that has a colored part to indicate the strength and sign of the effect. The user can change the size of the affected area with vertical movement of the mouse and the strength with horizontal while pressing and holding the middle mouse button. For a smoother feel, we implemented a Gaussian drop-off of the effect strength towards the boundary of the white circle. We were a bit over-ambitious with shortening, so we need to fix some areas. We can do this by relengthening the ray length again with a finer interaction setup. The now red-colored portion of the white circle indicates the flipped effect sign. We speed this up a bit. And here we see the result. We easily remove part of the skeleton. Next, we look at a micro-CT dataset of a silver scroll found at Yaraj in Jordan. Here we ended up tracing the contours in 64 cross-sections due to the complexity of the geometry. We connected the line segments to obtain an initial mesh, which was then further refined by remeshing and smoothing. Again, the flat mesh was obtained by a near isometric flattening of the curved one. Here we can see the resulting thin isosurface rendering of the dataset. We see that the technique allows us to obtain a view into the inner parts of the scroll. Writing was done by deforming the silver scroll with a stylus. The curved mesh only traces the general shape of the scroll, but not the fine protrusions of the individual letters. The effect is that the letters still stick out from the curved mesh, which is why we can see them in the rendering of the flat mesh. We can make this more clear by color overlaying the signed distance of the ISO value from the curved mesh. The mostly red color shows that the ISO value is in general found on one side of the mesh, but the bluely colored writing shows that here the silver scroll moves over to the other side, as illustrated in the sketch. If we now look a bit closer at some of the writing, we see that in regions where the windings of the scroll get close to each other, we start to sample in the neighboring layer. In these locations, we can use the local ray length adjustment in combination with the color overlay to improve the rendering. Here we could remove the artifacts. Finally, we look at a micro-CT dataset of an ancient papyrus package from the Nile River island Elephantine. This package was folded twice orthogonally. This time we chose a different approach for generating the surface pair. We started with the flat mesh and folded it twice according to the dataset. After folding, landmark-based deformation was used to fit the geometry closer to the structure of interest. We immediately see that this is not the optimal tool for this, as the deformation is often quite local. The general shape of the papyrus could be matched, although we also notice badly fitting areas, such as here or here on the inside. So how does a thin volume rendering look like? This is the flat mesh, and here is the resulting thin volume rendering. We see that it's not that bad. In many areas, the tracing was accurate enough so that the ray segments could sample the papyrus. The color map also reveals that there is some writing on the inside of the papyrus. Let us now turn to one of the holes where the tracing is of insufficient quality. We cannot simply increase the ray segment lengths, as this would cause a sampling into adjacent layers. Instead, we switch to thin isosurface rendering and overlay the distance of the ISO value to the curved mesh. Notice how the hole is framed with a deep blue color. This tells us that the distance of the ISO value is increasing as we approach the hole, and that we are indeed probably looking at an artifact due to the tracing, and not at a genuine hole in the papyrus. The sketch illustrates how this scenario looks inside the volume. Accordingly, we start to shift mispositioned vertices in the curved mesh along their normals in an effort to improve the fit. The interface here is the same as before, just the effect has changed. Once we're satisfied, we switch back to volume rendering, which reveals more writing. We can do this for the whole dataset until we are satisfied. In summary, we presented a data-aligned interactive visualization technique for thin volumetric structures that enables a holistic and unobstructed view onto originally curved structures. We showcase the technique for a variety of datasets from different domains. Furthermore, the technique allows for intuitive interaction and investigation tools that can be built on top of it. This was demonstrated by an initial set of 4 different techniques. The approach does have its limitations. Notably, the segment lengths do not change with the viewing direction. As a result, when moving the camera, subvolumes of different thicknesses are visualized. Desirable would be instead the definition of a thickness that is fixed for any location of the mesh. The transformation to linear segments on a curved domain can cause overlaps, which produces duplicated features in the rendering. We would like to investigate how transforming to nonlinear rays can alleviate this issue and possibly enable this technique for thicker curved structures. Thirdly, the technique depends on an adequate set of meshes. Producing these is a major bottleneck. Eventually, we would like to incorporate the presented technique as user interface into a framework that allows to interactively define the geometry of the structure of interest. For this, more sophisticated interaction tools than those presented here will be required. Finally, we would like to give our thanks to the people and institutions that supported the presented work.
Thank you, Felix. I noticed that we do have questions in the chat for your presentation. So I shall start off with a question from Anders Inneran, who says, I assume resolution in screen space will vary. How much and how do you convey that to the user?
Yeah, so that's exactly the right question. So when we deform the structure, we basically, we have to squeeze the volume, or we have to stretch it in some places. And right now, what we can do is you can just color overlay some kind of scalar field that lives on the surface. So you could basically, as a proxy, compute the curvature of the curved mesh and indicate this by a color on the flattened version and then mix it. So we have implemented this, and this gives you an idea of where seams are, where folds are, and where you have to be careful. But this is just a qualitative indicator, basically. We have worked previously with actually unfolding the volume and then computed an actual distortion map. But we have currently not no way of incorporating this exact information into this view. But yeah, you have this issue.
Okay, thank you. The next question was whether or not this tool could be used with higher dimensional data sets, for example, by combining with dimensionality reduction techniques. Have you thought about that?
No, I've not.
Could you?
What is meant by higher dimensional? So not scalar valued volumes or vector valued volumes, for example, or
no, but, normally higher dimensional is referring to many more dimensions on the input.
Yeah.
So if you had an R5 data set.
Yeah. So I've not thought about that.
I suspected you hadn't, but it was worth asking anyway.
Yeah, it might be an interesting use case. I don't know. Maybe if you have some interesting data, then we could think about that for us.
Alternately, we can recommend that the person who asked the question gives it a try for themselves.
Yeah, or just ask me. Maybe we can think about something interesting. So we just work with regular 3D volumes.
And that might be a profitable discussion to have offline over virtual beer. There's one other question that I see, and that is Noeska was saying that she really wants to try it herself on more data sets. And so she'd like to know if your tool is available somewhere.
Yeah, that's also kind of we have implemented a prototype in our visualization software that we use here at the Zuse Institute, and that's called Amira. And I think it's no problem to get a research license for that. If you have interest there, you can contact Daniel Baum. And yeah, we're currently in the process of getting this prototype into a state where it can be used by someone else than myself.
In other words, it's alpha code, and if you can live with alpha code, ask for it, and you can use it. Correct?
Yes.
Okay. I actually had a question for myself, and all of this is defined in terms of a locally flat sheet. What about closed surfaces?
Yeah. So we're thinking right now about, or we're working on extending this approach to so that you don't have to map the curved surface into a flat domain, so that you can have arbitrary curved surfaces as long as you have this, as long as you have the correspondence. So what you could do is you could map your closed curved surface to another closed curved surface that might be a little bit better suited for visual investigation. And for this, I think this method can be extended. But if you really, otherwise you are left with a problem, right? You need to cut open your surface somehow and map it into the plane.
Well, the example that I was thinking of was of the Golgi membrane in cell biology, which is very complex and isn't even guaranteed, if I remember correctly, to be genus 0. But you could see that sort of thing might actually be useful for exploring functional structures.
Yeah. But one compromise might be to just look at substructures of it that you can flatten out. But if you want to see everything,
So at the moment, the restriction to a flat sheet is a major, I shouldn't say a major, but it's a significant factor in how it's all set up, and generalizing that would be difficult.
Yeah, although you can, so the step to visualize it on another curved domain is possible. You basically would then, you need an intermediate flat
surface that you use as a parameterization for both curved domains or both curved meshes. And then you can use one curved mesh to look at and investigate another curve that traces your structure of interest. That works, but yeah.
But you're back to problems of texture parameterization in the first.
Yes.
That's about what I thought the answer was. Thank you very much. I believe we've now neatly run out of time, and I don't see any other questions. So
I have another issue. If anyone watching finds this project interesting, we have currently an open position for a PhD candidate. So if you like this, you can contact me or Daniel Baum directly, and yeah, we can talk about it.
Okay.
Thanks.
Thank you. And let's thank all of the speakers for an excellent session and go and have our lunch.